Alright, I just want to continue on with phase equilibrium diagrams. Let's make a system where we have a cylinder. Oops, make that, oh, went too far back. A cylinder with a piston on top. And of course, this piston can move friction. There will be no friction on the piston. It can move completely free. And it's going to be a constant, so it's the purpose of the piston is so that the system can be at a constant pressure. And we're going to assume the system is at 1 atm. 1 atm, or 1 atmosphere of pressure. So the piston is not only frictionless, it also has no mass. But we'll go on. We're going to say that also inside it, it's going to have maybe, oh, I don't know, maybe 1 mole of A, 1 mole of A, and also 1 mole of B, or 3 moles of B. Moles of B. Now, what the bottom of this graph shows, it has mole fraction. And we're going to say it's mole fraction of A. So the mole fraction of A in this system that we have created is just 0.25. It's a quarter. That also means that the mole fraction of B is 0.75. And what happens when you want to do that is you actually just go in the reverse from 1 to 0. So then we get 0.75. So for our system, we're just going to be interested in this line for now. And what we're going to do, we're going to start off at maybe 150 degrees. 150 degrees Fahrenheit. That's about right here. So we are right at this system. At that system, it is all liquid. There is no vapor. It's just pure liquid. Remember, anything under the saturated liquid line, liquid is just a liquid. They call it a subcooled liquid or a compressed liquid. So at 150, the system is completely liquid. 150 liquid. We're going to move up then by increasing the temperature of the system till we get to the saturated liquid line, and we'll say that's maybe around 200. So at 200 degrees Fahrenheit, 200 degrees Fahrenheit, it's mostly liquid, but some vapor, a very small amount of vapor. It's when you're at the saturated liquid line, there's just a tiny amount of vapor. If we were to continue upwards to maybe 250 or 210, 210 degrees, 10 degrees Fahrenheit, now it might be, actually let's do the calculation. What you use to calculate the vapor in a system is you actually find out this distance and this distance. So right here to right there, and I think, we're going to say that's, even though it's not, we're going to say it's 1 centimeter, and we're going to say that this is 2 centimeters. So the total distance is 3 centimeters. But for the liquid component, you get you use the inverse lever rule. So you use actually 2 divided by 3. So 2 divided by 3. 2 divided by 3 is the liquid. So of our system, 2/3 of it is liquid, and actually 1/3 is vapor. And that's just because this distance right here is 1 centimeter, and this distance right here is 2 centimeters. So, and what so when you're closer to this line, you're more liquid. Your system has more liquid in it. when you're closer to this saturated vapor line, it has more vapor in it. So if we were to continue up to maybe 220 degrees Fahrenheit, 220 degrees Fahrenheit, our system now is mostly vapor, but some liquid, very, very small amounts of liquid. I mean, if you use the inverse lever rule, you'd say maybe that's 2.99 centimeters, and it's 3 R. That's actually a little less, but you'd measure this distance and this distance, and it'd be basically 0.9999999 vapor and maybe 0.00001% liquid. So if we were to continue to increase the temperature of our system, again, it maybe got to 250. So 250 degrees Fahrenheit. Our system is now all vapor. All vapor. So that at that point it's completely vapor. They call it a superheated vapor, I believe is the term. And so that's just the basic. I'll run through it one more time just really quickly. When you're in this area, you're completely a liquid. When you're touching this line, you're almost all liquid, but there's a little bit of vapor. When you're touching this line, the saturated vapor line, you're almost completely vapor, but there's a small amount of liquid. And when you're at the very top, up here, you are completely vapor. And remember, the system is all at 1 atm. This would look different if you increase the pressure to 2 atmospheres. It wouldn't be this anymore. So this is at constant pressure, and we're changing the temperature. And remember, at 250 degrees, we're changing the temperature of the entire system, not just the vapor, the entire system. So I said that at 210, it's a little bit of liquid and a little bit of vapor, but the liquid and vapor, they're both at 210 degrees Fahrenheit.